Good evening, everyone, and welcome to another episode of Anatomy Action News, where the stories are tiny, the drama is constant, and the reporters are somehow always inside an organ. Tonight, we're bringing you a fully loaded broadcast covering the sensory system from every angle: touch, taste, sight, sound, and even the mysterious forces keeping you from walking into furniture. We've got breaking updates, undercover receptor operations, financial reports from inside the bodies, and an exclusive look into the eye and ear. So buckle up, because the human body has never been this dramatic. We have urgent breaking news from inside the human body, reports of sensory chaos and possible pain activation. We have our reporter Martha on the site ready to give us the update.
I'm here reporting live from beneath the skin, where unencapsulated nerve endings are firing wildly. Now, these unencapsulated nerve endings are those that are exposed sensors with no connective tissue wrappings around dendrites. These include free nerve endings, tactile discs, and hair receptors. You can almost hear the alarms from here. Not to be outdone, however, by the encapsulated receptors, which are also playing a role. Tactile, bulbous, lamellar corpuscles, end bulbs, muscle spindles, tendon organs, these are all fibers wrapped in glial cells or connective tissues, and they are also stepping in with reports of vibration and pressure. Next, I can confirm that pain signals have gotten involved. Nociceptors have officially declared a national emergency. They've launched two waves: fast pain, which is sharp and immediate, currently moving through myelinated fibers, and more slow, aching pain, also moving, but more so through unmyelinated fibers. Both are climbing the classic three neuron pathway towards the cerebral cortex to start their effects. Some are traveling from the head through cranial nerves, and others are traveling through spinal tracts. Next, I can confirm that referred pain is also occurring. That is pain that's felt in a different part of the body from where the source actually is. And this is due to nerve pathways in the nervous system overlapping, and multiple regions are currently sharing the same pathways, leading the brain to be confused about where the pain is coming from. Hello? Hello? Oh gosh, we have breaking, exciting news. The brain has officially deployed its natural defense team, endorphins, enkephalins, and dynorphins. They're chemical fighters to lower this pain. Things are really looking up for us. Plus, I just got word that the spinal cord has started their pain gating system, which is trying to block excess signals before they surge upwards. This is a great sign. Now, that's all we know for now. I'll keep you guys posted. Make sure to stay tuned and stay safe out there as we fight this pain.
Thanks, Martha. And now for our next story, we're heading over to Bella, who's diving deep into one of the most underrated teams, keeping your body alive and functioning. These unsung heroes are on duty 24/7, reporting everything you see, hear, touch, taste, and smell. Basically, the body's own undercover intelligence squad. Bella's got the full scoop on these sensory super spies, so let's hand it over to her. Bella?
Hey guys, so today we're going to be talking about sensory receptors, basically the tiny FBI agents of your body. This whole job is to spy on the world around you and report everything back to your brain. Some receptors are simple, like bare nerve endings that are just vibing until you touch a hot stove. Others are super dramatic and fancy, like your ears and your eyes, aka the Kardashians of our sensory system. Every receptor does this magical thing called transduction, which basically means turning life into electricity. Light, electricity, sound, electricity, touch, yep, electricity. Your brain is basically a giant electrical drama queen. They work in two stages. First, sensation, which is your receptors, they go like, hey, something is happening. Second is perception. When your brain finally decides, okay, I'll pay attention to that. This is why you forget your clothes existing like after 5 seconds. Receptors send four things to your brain: modality, location, intensity, and duration. Modality, what is it? Light, pressure, or pain. Your brain knows based on the wire the signal comes in on. If we rewired your nerve from the ears to your visual cortex, you'd literally see sound. Imagine hearing someone yell and your vision just flashes like a disco ball. Location, where is it happening? This depends on receptive fields. On your back, one neuron covers like a whole country, so two pokes may feel like one. But your fingertips, those receptors are packed tighter than people at a Black Friday sale, which is why you can feel every tiny detail. Intensity, how strong it is. Your brain figures this out based on how fast the neurons fire and how many join the party. Weak stimulus equals one shiny neuron, and strong stimulus equals a full rave of neurons. Duration. How long is it happening for? Receptors adapt. This is why hot showers go from I'm being boiled alive to yes, perfection in 10 seconds. There are different types of receptors too. Thermoreceptors feel temperature, photoreceptors are light, nociceptors scream pain, chemoreceptors handle taste and smell, and mechanoreceptors sense touch and pressure, basically all the poking, prodding, and stretching chaos. We also have exteroreceptors from outside stuff, interoreceptors for inside stuff like your stomach complaining, and proprioceptors, which are the MVPs that tell your brain where your body parts are so you don't have to walk into door frames. Generally, senses are everywhere and simple. Special senses are the fancy ones: vision, hearing, balance, taste, and smell, the elite private school of our sensory receptors. And that's it. Sensory receptors are the tiny creatures working overtime so that you don't fall over, burn yourself, or miss someone calling your name. Respect them, they are tired.
Great scoop, Bella. Let's head over to the body business report with Joseph. Down to you.
Good evening, I'm Joseph Foxrider, and welcome to the Body Business Report. I'm your host, bringing you the latest updates from the booming chemical senses industry, where taste and smell dominate daily operations. Let's start with the taste division. Taste buds are sensory processing units operating across the tongue, the soft palate, the pharynx, and even the epiglottis. Each bud contains gustatory cells, supporting staff, and basal stem cells, keeping everything running smoothly. You could say these are high efficiency micro offices. These buds are located on the lingual papillae. As you can see here, papillae or filiform papillae are everywhere, but they don't host taste buds. They handle texture. Think of them as the HOA of the tongue. Fungiform papillae are scattered, mushroom-shaped units, each with a few taste buds. Foliate papillae sit along the sides, especially active in young individuals. And finally, the valate papillae, the big bosses at the back of the tongue, each housing hundreds of taste buds. The flavor market remains dominated by five primary products: sweet, salty, sour, bitter, and umami. But flavor isn't just about taste. It's also shaped by smell, texture, and temperature, and even your emotions as well, ensuring that every bite is a multi-departmental collaboration. Now, how do chemicals activate the taste buds? Sugars trigger GPCR pathways like VIP access. Salts enter through sodium channels, a direct walk-in approach. Acids deliver hydrogen ions that disrupt potassium channels, forceful entry. Bitter compounds use GPCRs with high specificity, strict security protocols, and glutamate, our umami agent, binds to receptors, producing savory satisfaction. Taste signals leave the buds via three cranial nerves: facial, glossopharyngeal, and vagus. They travel to the uh, solidarity, solitary nucleus in the brainstem, pass through the thalamus, and finally arrive at the gustatory cortex in the insula and frontal lobe. Turning now to the olfactory sector, the olfactory mucosa high in the nasal canal contains receptor cells specialized to detect odor molecules. When odorants bind, the cells fire via G protein cascades, sending the electrical signals along cranial nerve 1 to the olfactory bulbs. From there, reports are distributed across the brain's executive offices, the temporal lobe for conscious perception, the insula and orbital frontal cortex, integrating smell with flavor, the hippocampus for smell-associated memories, the amygdala managing emotional responses, and the hypothalamus coordinating visceral emotions visceral reactions. Even the cerebral cortex exercises top-level management, fine-tuning sensitivity, and influencing perception. So that's today's body business report. Taste and smell remain fully operational, networks running efficiently, and your brain continues to ensure top-level oversight. Thank you for tuning in, and remember, your chemicals senses are always on the clock. Have a good night.
Fantastic, Joe. The next segment is actually covered by my twin brother and takes a deep dive into the anatomy of the eye. Take it away. Here we have the anatomy of the eye. So as you can see, this is an eyeball. We have the three layers from the outside to in. You have the sclera, which is the white part of your eye. You have the choroid and then the retina. Then also back here you have the optic nerve going through with the central vein and artery. The central vein and artery is key to supplying blood to the eye as has functioning tissues and cells that need to be kept alive. The optic nerve is what allows us to see. I believe this is cranial nerve number 2. And then you have your optic disc also in the back, which is the blind spot. Moving to the front of the eye, you have the cornea, which directs light into the eye to hit the lens. As light hits the lens, it's going to bend it to the optic disc. And then you also have the posterior chamber, which is behind the ciliary body, and you have the anterior chamber, which is in front. The ciliary body holds the suspensory ligaments, which are going to keep the lens intact. The iris is the colored portion of your eye. And then the pupil is what constricts and dilates to either let more or less light in from the cornea based on your surroundings. Thank you. All right, you have 2 disorders of the eye. First one's myopia, which is nearsightedness. So objects close are going to appear clear, and objects far are going to be blurry. This is because the image focus point is in front of the retina, and as a result, your eyeball is too long. The opposite is hyperophia, which is farsightedness. Far objects, in this case, are clear, and close objects are blurry. And again, this is due to the image focus point being behind the retina, and the eyeball is too short. Wow, that was some really great stuff. You were always the favorite child. Anyways, our last segment comes from reporter Luca, who will be taking us through the anatomy of the ear and process of hearing. This segment covers the ear, the outer ear, middle ear, and inner ear. The outer ear's role is to collect sound waves, thanks to its shape. From there, the waves enter the external ear and strike the tympanic membrane, setting it into motion. This membrane is connected to the malleus and connected to the incus, which is connected to the stapes. This causes a back and forth vibration of the stirrup, which is connected to the oval window. Then causes fluid vibrations in the inner ear, which travel to the scala vestibuli. They go around in the cochlea and arrive in the scala tympani before it strikes a pressure-releasing membrane known as the round window. Here is an image that depicts how sound waves are converted mechanically in the middle ear into fluid waves, which then are picked up by the cochlear nerve. Another important part of the ear is the auditory tube. This allows us to maintain the correct pressure in the ear, and if the ear is filled with fluid, it allows us to drain it. Here's the cochlear nerve. This is the nerve that picks up the sound waves that are converted into fluid in the cochlea. Another important part of the ear is the vestibular system, which is made up of 3 semicircular canals positioned in 3 different planes. It detects movement of fluid inside these canals whenever the head moves. It causes the bending of tiny hair cells, which send signals to the brain, helping the body stay balanced and correctly oriented. These signals are detected by the vestibular portion of the vestibular cochlear nerve, which sends the information to the brain. Well, that's that. Thank you so much for watching, and always remember to tune into your weekly news of Anatomy in Action.